Hello, everyone. This is Michael E. Yeaman with another Geology of Sculpting Stone presentation. Today, Columbia River Basalt. And why should you care about the geology of your stone? Well, stone sculpture is one of the oldest art forms and dates back to the very beginning of art history. And the story of our stone is unique. Therefore, knowing more about the geology of your stone will allow you as stone sculptors to select specific stone types that have a compelling history for both you and your viewers. You can marvel at the stone's various elements of color, texture, composition, etc. as you work it. You can consider how the sculpture's chosen artistic form, your artistic form, will relate to the actual science of the stone. And finally, you can weave into the final artwork a geologic story, a component that actually enhances the interest of your particular piece for both you and potential buyers. And as usual for the Geology of Sculpting Stone series, we have three major areas we'll take a look at. One, the stone defined, a specific geologic description, chemical properties, and historic use, specimens, both large scale and small scale, and specific occurrences of where you can find the stone. We'll take a look at the geology, its age and description, its formation environment, and the processes occurring, where the global geographic, paleogeographic settings were for this stone, and any modern analogs of where we might find stone of this type forming today. And finally, we'll take a look at select creations both in art and architecture. So let's dive into the general description of our stone, some of its physical and chemical properties, and its historic use. Well, the Columbia River Basalt, the basalt group that gives its name to this series of dark volcanic rocks, was an area that was flooded with these surface lavas in southeast Washington, parts of adjacent Idaho and Oregon from about 17.5 to 6 million years ago. The thickness of the Columbia River basalt, and we'll abbreviate it as CRB from now on, goes from near zero at the edges of the Columbia Basin to over 10,000 feet thick at its center. The CRB is generally homogeneous chemically, has a tendency in general to be dark brown to black, and weathers to a medium brown rough rind, where some of the ferromagnesium minerals will actually weather to produce that color. Unlike most basalts, the CRB has a high percentage of quartz in it as its main component. Many basalts have a much smaller amount of quartz. The Grand Ronde member is close to an andesite, which is almost a highly quartz-oriented mineral. In addition, it contains several dark minerals, hornblends, pyroxenes, biotite, olivine, magnetite, many other ferromagnesium minerals which give it its distinct colors and characteristics, and some feldspars. It's a medium density and has a tendency to fracture conchoidally, which means it fractures as circular patterns, much like broken glass. If you take a look to the right, you can see the chemical composition of the CRB, and you can see that the silica dioxide component, i.e. the quartz component, is nearly 54%. That's rather high for a lava, and contains a lot of other minerals in it. There's the aluminum, iron, magnesium, calcium, sodium, potassium, titanium, phosphate, and manganese, all the way down from about 11% down to just a less than a tenth of a percent. But these minerals add a lot of character to the CRB and make the Columbia River basalt as special as it is today. It's been used locally since the 1800s, most commonly crushed for aggregate industrial and construction projects, but it's also been used for dimension stones, for walls and tiling, occasionally veneers. We'll talk a little bit more about that when we get into the art and architecture use of the CRB. So here's some pictures at the macro level, the big scale level. Outcrop here in Eastern Washington, a place near and dear to my heart. I grew up in Eastern Washington in Yakima, in the dry areas of the high desert of Eastern Washington. You can see in the outcrop it has this very distinctive plateaued layered element with the vertical columns in it. We'll discuss a lot more about that in a minute. Hand specimens here in the upper right, you can see the sharp breaks and a little bit of the conchoidal fracture. We'll talk more about that in a little bit here in a few minutes. Here's some prepared slabs in the lower left and some quarried columns. And we'll talk a lot more about how columns form in the CRB a little bit later in the presentation. With the Columbia River basalt, you have very distinct characteristics of the stone, depending upon whether or not it's rind, you're showing its split face, or a polished surface. The rind here shown on the left is this rugged characteristic where oftentimes it's off brown to grayish, and it's produced by the dry weather in eastern Washington after the exposure following the flooding, which we'll talk about a little bit later, that exposed a lot of the basalt. And it is very distinctive, makes up the color palette of pretty much all of eastern Washington where the rock is exposed. In the front here, you can see this split face on this bench, and it is very distinctive. Here's some elements of what we talk about, this conchoidal fracture, this circular fracture characteristic where you break the stone and has kind of a gray hue to it, very clean breaks to it of this circular nature. And finally, the upper polished surface, you can see the reflected blue sky and the tree in this, but if you were to stand right above it, it oftentimes polishes to a very beautiful mirror-like black to dark brown. Now here in thin section, I've taken a piece of the CRB, or actually I didn't, it comes from a local lab here. And again, a thin section is just a very thin section cut in the stone, which allows light to shine through it. And when you get light shining through a thin section, oftentimes it helps you identify the minerals or the other things that are happening in the rock. So in this case here, you can see a couple of different things happening. I'll point out here that on the upper right, as I make mention of something called a vesicle, which is basically just a gas bubble, and we'll talk about why there's gas bubbles in the CRB. Here's one of these accessory minerals, pyroxene, I mentioned here with the arrow that points over to this large squarish block of rock here in this thin section. And the lighter colored minerals in the slide are mostly feldspars, as pointed out here by the arrow pointing to this angular piece here towards the lower right-hand portion of the slide. Basalts oftentimes are quite colorful in thin section because they contain all these different minerals we just discussed. If we take a look at a couple more thin sections, in a couple of different places in the lava flow that makes up the Columbia River basalts, one from a place called the entablature, when we'll talk more about where that is in the flow, and compare that with something, a thin section taken from the colonnade, which is towards the bottom of the flow. And you can see that there is some distinct characteristics. Here it's all in black and white, so we won't be able to see some of the sharp mineral differences, but you can see, for example, in the colonnade, the crystals seem to be a little bit more developed here than they are in the entablature above, and the same to be said in this other thin section development down in the colonnade compared to the entablature. A couple of different types of light showing through this thin section to give us these views. Finally, let's take a look at a couple more thin sections, one from the entablature, again, upper, and one from the colonnade lower. Here, they're abbreviated identifications of some of the mineral components as identified by mineralogists here, looking at these thin sections, the light-colored grains being the titaniferous magnetite, MT, magnetite oftentimes being a black mineral that shows up in many igneous rocks, some medium grain pyroxenes, some plagioclase feldspars, and some volcanic glass in a fine grain ground mass, all labeled there by the various abbreviations that show quite a bit of variation here between the entablature and the colonnade and thin section. Now, what about the specific occurrences? And specifically, what about other places like the Columbia River basalt? Well, the Columbia River basalt is a special type of basalt. They're called flood basalts, and they're areas where in the Earth's past, major outpourings of lava occurred over vast areas geographically. And here we've listed some of them. We're going to be talking today about the Columbia River basalt and about the tectonics that produced this large mass. But you can see some other really large ones here in southern Brazil, Ethiopia, the highland basalts of Ethiopia, some rather famous older basalts here in South and Southeast Africa, the Karoo basalts, And then finally, two very important ones geologically that have affected the Earth's climate and evolution of land and plant animals. The Deccan traps, a trap being just a name for an area where these basalt floods occurred, and then finally the Siberian traps. Both of these were actually tied to major extinctions of animal and plant life. The Deccan traps being related to the time when the dinosaurs disappeared, and the Siberian traps being very close in age to the mass extinctions occurring at the end of the Permian. Two important times where there seems to be direct relationships to the outpouring of these large volcanic flows and the changes in the Earth's atmosphere affecting life on the planet. We'll spend a little bit more time in the future talking about that here as we go into the presentation. Also, specific occurrences, let's drill down a little bit more in our own CRB area. Here is a picture of Washington State with a little bit of Oregon and Idaho. Here in the shaded area is the distribution of the Columbia River basalts, and you can see they occupy a zone that covers all of southeastern Washington, a little bit of northeastern Oregon, a little bit of Idaho, and actually they extend down the Columbia River all the way out into the Pacific Ocean. We'll talk about why that's the case as we get down to it. You can see they occupy about 63,000 square miles, huge, one of the larger basalt flows in the Earth's history, occurring fairly recently geologically, only 10 to 15 million years ago. And as I said, in places they can have flows go quite thick. This says 6,000, as I mentioned. Other places, perhaps as thick as 10,000 feet. Now, probably the Columbia River basalts occurred in over 300 individual lava flows, which have been identified by geologists working in Washington and Oregon. And they probably also had numerous smaller flows. They were long linear vents that produced these flows, mostly sitting in this area of southeastern Washington and northern Oregon. Along these big vents is where the large amounts of lava would come to the surface and flow quite quickly, covering large areas geographically. And frankly, as all these flows began to accumulate, the load, the weight produced by all this lava pouring out of these vents weighed down this area of the Earth's crust in this area of southeastern Washington, northern Oregon, and actually caused quite a bit of subsidence, which allowed additional lava to accumulate over the years. And actually, to this day, is a very interesting phenomena that of geoloading produced by these large basalts. And I've also shown here a couple of different spots where we have some rather significant volcanoes from Mount Jefferson up to Mount Rainier and beyond. These volcanoes really have nothing to do with the basalts themselves. They're just much more recent phenomena unrelated to the Columbia River basalts. So I want to include one more map here, a rather busy map, a map of the geology of Washington State. But I want to point out that there's a lot of information on this map, but we want to focus is on the area down here in the southeast corner of the state, makes up about almost a quarter of Washington State. And you can see the geology here is a lot more simplified at the surface because you can see it's just a couple of colors which represent recent sediments. And that corner here is the area where, again, 10 to 15 million years ago or so, the flood basalts came out and basically buried all the other geology of Washington State underneath them, leaving this more simplified geologic map view of the area. And here now I've overlaid on top of it the location for the very thick sections, at least, of the Columbia River Basalt group. And you can see it fully occupies this big corner of southeastern Washington State. And as I mentioned, parts of northeastern Oregon and a little bit of Idaho. Okay, in the area of the Columbia River basalts, I wanted to point out how they are focused mostly in southeastern Washington State, but the lines here on this map are a series of faults and anticlines, which it's a block of rocks that's been folded up in a dome-shaped style. And you can see a lot of faulting in and around the Columbia River basalts. And there's a couple of different things that are worth noting here. Once again, you can see that the extent of the basalts, as I pointed out, is mostly in this corner of southeastern Washington, a little bit of Oregon, but there is this interesting area down to the south of Oregon in the Steens area. We'll talk about the importance of that a little bit later on, but I also want to point out where it says the primary dike and vent and swarms. These are the areas here in southeastern Washington over into Idaho where a lot of the basalts that make up the Columbia River basalt group are believed to have vented or flowed out of and resulted in those massive thicknesses of the Columbia River basalt that filled in this corner of southeastern Washington up to 10,000 feet in thickness. And the distribution, as I mentioned, now recognized to occur over a much broader area, really implies a little bit about what might have produced the basalts. And we'll talk a little bit more about that in the future, but it's part of the evolving picture of plate tectonics over the last 30 years, and specifically how a big mass of liquid lava can actually accumulate and flow to the surface to produce these large flood basalts. So on this map, which is called an isopack map, an isopack being the thickness of a geologic unit, we see this bullseye look here in southeastern Washington. And as we talked about, that the Columbia River basalts get as much as 10,000 feet thick. This contour in intervals in meters, but it converts to about 10,000 feet of thickness. And it's sitting here in the southeast corner of Washington State. And the element of the bullseye just simply implies that the settling that we mentioned before, occurring as the basalt thickened and weighed down the Earth's crust, basically causing a shallow low that filled in with additional flows coming from these vents. It implies that this bullseye thickness of the Columbia River basalts is represented indeed by this subsiding unit that filled in this section of southeastern Washington. So here we now have a detailed stratigraphic column. Now, what a stratigraphic column is, it's strictly a list of the various types of rock in a vertical sense, from more recent being on the top of the column, older rock being on the bottom of the column. And here, over the last 100 years or more, of detailed mapping of the Columbia River basalt group, they've arrived at all of these subdivisions, splitting down these individual flows into major groupings here. And there's a lot of information in this chart. I think the thing to center in on, as far as the interest here for our geology of sculpting stone, is that, as I mentioned before, the CRB erupted between about 17.5 and 6 million years ago. The different names of the basalt subcategories are listed here. The Grand Ronde, we've talked about that before, has a great thickness, and you can see that as a member here in our stratigraphic section here where it says, I'll circle it, Grand Ronde basalt. And you can see that it is sitting down near the beginning of the flows, around 17 to 15.5 million years ago. And you can see as a percentage of the overall basalt group, the Columbia River basalt group, it makes up 87%. So the big chunk, the majority of the lava that came out to form the Columbia River basalts happened back during this Grand Ronde time of about 17 to 15.5 million years ago. And a lot of other different units have been identified. One thing to point out here is the great thing about basalt is because it contains all this ferromagnesium minerals, which are very much responsive to the Earth's magnetic field, is that they can actually see times when the Earth's magnetic field changed based on measuring the alignment of the ferromagnesium minerals in the basalt. So that gives them another way to map them, and you can see here MAG representing the magnetic polarity during when each one of these members, whether normal or reverse compared to today. Anyway, it just provides another way to actually map very carefully the components of the Columbia River basalt. Um, I should point out a couple more things I do here on the right. The flows were semi-continuous over this period of time, so very little erosion seems to have taken place between the flows, and that's partly because it's a rapid accumulation, and with a few exceptions, there isn't a significant erosional unconformity between these flows. There is occasionally areas, however, that did develop a little bit of fossil soil on them. And sometimes those fossil soil contain fascinating fossils within them of the animal and plant life, which also help date the flow and suggest what was going on between these periods of volcanic activity producing these big flood basalts. Here's another little interesting graph, I think, where it comes with a distribution of the volume of flow based on the flow type here. We talked about here about if we take a look at the Grand Ronde basalt member of the Columbia River Basalt Group occurring here in this period of time, you can see that it makes up a huge amount of volume in cubic kilometers of the actual lava that came out, with a lot of it occurring between about 17 peaking and then coming back down around 15 million years ago, with different names of flows are on here, but lasting all the way up until 5 million years ago. And then here is just a little bit of a map where the different minor mineralogical components within the individual basalt units can be mapped out. So you can see once again our little Grand Ronde member here, which makes up 87% of all the flow, has a rather distinctive mineralogical components of this titanium oxide and some of the phosphorus, potassium oxide material, actually phosphorus oxide material that occurs, which allows them to differentiate the individual flows by these subtle variations in these minor mineralogical components. Anyway, just an interesting map allowing geologists to pick apart the massive amount of Columbia River basalts, individual flows occurring at individual times. So let's take a look at some outcrops of the Columbia River basalt group. And what geologists love is that they love a spot where there's really no modern life growing, because frankly, plants just get in the way of a good outcrop. That's our old opinion as geologists. And so Eastern Washington is a great spot to do geology because it's so dry and most of the vegetation is reasonably thin. And so therefore you can actually see the rock outcrops pretty readily and allows you to geologically map them in a much more easy way than if you say were outside of Bellingham in the middle of a rainforest with all those nasty trees in the way. But anyway, here what we have is a map of some of the components listed by the various geologic sub-members of the Columbia River basalts. Here we have down at the bottom our old favorite Grand Ronde member here at the base of this cliff, up to the Frenchman Springs, the Rosa member, and Wanapum basalt near the top. And you can see that each one of these has kind of a distinct layer, almost like a big layer cake. And of course, lava and basalt flows are igneous rock, but the way they're deposited has a lot of sedimentary characteristics in common, i.e. as flowing material that eventually, in this case, solidifies and forms individual units. And so a lot of sedimentary geology and extrusive or lava-based igneous geology has some depositional characters in common. And we'll talk a little bit more about that as we look more at these outcrops. Oh, here is also some pictures I added in here that give you a little bit more of a description of the outcrops. These columns that are very common in Columbia River basalts, you can see here from the surface, and they have this hexagonal pattern of jointing in them or breaking the rock apart. The ones on the upper left, you can see that hexagonal shape quite readily. The ones here on the right have more of a weathered top to them. And then, as I mentioned before, some of these columnar basalts in the Columbia River Basalt group have gas pockets in them. We call those vesicles. And here is on the lower section photograph, a wonderful picture of one of the Columbia River Basalt rocks, probably rolled around in a river to give it this round shape. But the vesicles are so apparent here, big open spots where gas that was initially trapped in the lava as it came out the vents escaped and left behind an air pocket or a vesicle. Very pretty piece. Now let's talk a little bit about the formation environment and processes of the Columbia River Basalt Group. So all basalts, but particularly flood basalts, when they have a perfect or idealized flow, will have these components. And they'll go from a zone below, which if it flowed out into water may actually produce pelobasalts. We'll talk about those a little bit later. Then they'll have a section as the lava begins to cool after it flows, form these vertical columns. They're called the lower colonnade section of a flow. Then above that, these columns will have a tendency to fan out, not be perfectly vertical. They will oftentimes fan out like a flower or a growing plant. Those fanning columns oftentimes occur at the bottom of a section geologists call the entablature. Above, as you move in the upper portion of the entablature, there'll be hackly or slender columns, not nearly as distinct as the lower colonnade. And finally, there'll be an upper colonnade, which will have some of the characteristics of these large columns like the lower colonnade, but not be quite as blocky or subdivided. And then if it's preserved at the very top, these vesicles, air pockets escaping from the top of the flow as the gases bubble up through the flow and escape into the open air, will be at the very top of the flow, the vesicle flow top. And we have here on a thickness, for the Columbia River basalts, it can be 100 or a few 100 feet of section, both in meters and obviously more if it was measured in feet. And so these are not giantly thick sections, but they are substantial. But they almost all, when they're preserved, will have these components from the lower zones of the colonnade into the vesicle flow top. And here I've done now a series of photographs that show the various components. I'm going to roll through here: vesicle top, the upper colonnade, the entablature. I've had to composite this to get all the pieces shown, but here's the lower colonnade, maybe with some of these lower pellet zones at the bottom of it. And so here in this composite photograph, we have a series of outcrops from the lower pellet zone up through the lower colonnade, the entablature, upper colonnade, and vesicular top. As you can see, since I had to composite these photographs, it's not oftentimes where you find an outcrop that contains an exposure of all these elements in one outcrop that you can get in one photograph, but these two individual photographs capture pretty much all the elements. Now, as these flows occur, let's talk a little bit about the dynamics of the flow. The growth and inflation of these lobes of lava as they're ejected from these tubes results in sort of a standardized pattern as the flow occurs, in this case, across southeastern Washington, forming our Columbia River basalts. So during the initial flow, and oftentimes measured out in hours, the lava will break out and begin the flow across the surface. And that flowing rate has been measured based on a couple of different factors, perhaps to be as fast as tens of miles an hour. So these flows can really get going. They'll have a harder top, signified by this darker color, and then the active flowing element will be down in the lower portion of flow as it moves, in this case, from right to left across the surface. Then in upper right here, in number B here, our picture, the inflation or the growth of the flow will begin to occur. That a period of time can be in days or perhaps even years, where the molten core, which we talked about before, continues to flow out. And above it is developing more of this brittle crust, where a little bit of the molten core can begin to break out, perhaps in new areas, and keep the brittle crust what a geologist term as viscoelastic. It just means it can flow a bit on top of this molten core. By the time you've reached a more of a stagnant flow here now in C, a picture of the lower left, the flow, active flow is stopped now, and now it's beginning to solidify or freeze after the flow stagnates. This freezing period or solidification process from molten to solid can occur over months or perhaps as long as decades. And then finally, at the very end, when all the solidification has occurred, and now we have solid rock from top to bottom. We have our standard frozen lava flow, which we just took a look at in those photographs on the previous slide. Now, sheet flows, this specific type of really massive lava flows that are part of the Columbia River Basalt group, occur in only those areas we mapped around the world, at least that we see in present day. And they have rather distinctive differences between composite flows, which can occur over a series of discrete events, much like a volcano erupting. So here I'm showing a difference in characteristics between a sheet flow, like our Columbia River Basalt groups, large lateral flows, perhaps thinner in many areas, but extending over large areas with the continuity in the flows being able to be mapped from tens, if not hundreds of kilometers, versus distinct compound flows with individual blobs or units of lava that would come off of individual vents, or like in the Pacific Northwest, volcanic elements that produce point sources of the lava. And as I mentioned, the Columbia River Basalt Group sheet flows have a different internal makeup than a conventional point source like a volcano. So let's spend some time taking a look at the formation processes of the Columbia River Basalt. And specifically, a lot of the new elements of our understanding of what went on in their development are really quite recent, the last 20 years or so, and they make a fascinating story. So let's spend some time and see if we can figure it out. So here we have our standard plate tectonic model in a 3D version. If you recall from previous plate tectonics conversations, we have the idea of a subducting plate that's diving down between underneath North America. And as you know, in our previous discussions about plate tectonics, that oftentimes things get scraped off the plate and they get bubbled up and formed into volcanoes like we see in the present Cascade Range, where we get volcanic eruptions. But we talked about how our flood basalts were not like these. They're different. So here's how they think they formed. The plate continues to subduct. They do get additional melting that occurs off the top of the subducting plate. That melt produces, in this case, a large amount of lava ready to flow to the surface and break out. But here we seem to have a rather distinctive pattern that this accumulation of melt seems to have occurred in more of a circular or spot kind of a distribution. In fact, geologists have a tendency to call these areas that produce these large circular melts of lava that comes to the surface as hot spots. So let's take a look at a little bit about what a hot spot looks like for the Pacific Northwest. So let's begin by tracking down what we mean by a hot spot and why it's so important for the Columbia River basalts by this map. So you recall, here's a map of the distribution of the basalts. We talked about how most of them are located down in this area of Washington, Oregon, Idaho. And we think that they came out of vents, or oftentimes called dikes. And here is listed a group of them called the Chief Joseph Swarm of dikes, which occur in this approximately this area. And we think that's where the majority of the Columbia River basalts came from. But a while ago, about 10, 20 years ago, increasing interest began to occur in this area of also dike swarms in southeastern Oregon called the Steens Dike. So some of the same age basalts occur, although much thinner, down here in southeastern Oregon. So if we take a look at what a formation process of one of these large molten blobs that has come up from the upper mantle of the earth and flowing to the surface to come out onto the surface of those volcanoes, here we have a distribution and a map of the evolution of what the blob, the hotspot material of the Columbia River basalts may have looked like over time. And here we have a development from about 25 million years here on the lower left as a pictorial version of this little blob beginning to come up through the mantle all the way up to just the 10 to current day. And what you see here is the mantle material coming up as a general oval or tear-shaped form. But then as the plates began to move over the top of this, geologists believe that the head of this mantle plume may have begun to be distorted or moved around by the movements of the plates themselves. And that what they call this lithospheric plate motion may have distorted the location of where this mass or blob of magma, liquid volcanic material, may have been able to come up through a series of vents to the surface. And therefore, we would expect to see the location of those vents move over time. And then finally, as we reach present day, and the location of the plates has moved, the flood basalts, at least in the southeast Washington, Oregon area, have now died out. But here's something kind of interesting. So this is a fairly recent map that talks about the plume head or the top of this magma body and its direction and motion relative to the top plate over time. And here you can see that it's believed that this began in southeastern Oregon, but that the plume head itself might have been distorted and brought up into the southeastern Washington, Oregon area where the Chief Joseph Dike swarms released a lot of that magma that was in that plume head in creating the Columbia River basalts here of southeastern Washington and northeastern Oregon. But the original mass, the location of the plume itself, left enough behind of the plume. We saw that plume stretched out in the previous slide, that as the North American continent moved to the west, and I'll give a big arrow here showing the direction of the movement, the resultant would be the appearance of the hotspot, the plume itself, moving to the east, right? In other words, the hotspot itself didn't move. It's the plate over the top of it that moved to the west. And therefore, the hotspot track, the track of that plume, might be expected to move to the east. And that's exactly what we see here across the Snake River area of southern Idaho, to the point now where the plume tail, the very remnant piece of that plume now, is located right underneath Yellowstone National Park. That has all sorts of implications, nothing related right now to the Columbia River basalts, except to this story I just told, but it makes a story about why those beautiful hot springs are available in Yellowstone. So here is another map showing the movement, relative movement of this hotspot with time. Remember, North America is flowing to the craton of North America is moving to the west, and therefore the hotspot itself is going to look like it moves to the east. A lot of geologists believe that hotspots may be rather fixed with respect to the upper mantle, and that seeing things move over time was related to the plates themselves, the thin veneer of the plates moving. But here you can see that beginning about 16 million years ago, there was a distinctive pattern in southeastern Oregon. And then as we become closer and closer to the surface, or excuse me, to the present, then you can see the appearance of this hotspot mapping a series of calderas or volcanic vents and some volcanic craters that track right across the Snake River Plain. In fact, are definitely related to creation of the Snake River Plain and the volcanics we see there, all the way over here to the corner of Wyoming, right underneath Yellowstone, where the plume material gets close to the surface, and we have things like Old Faithful. So, paleogeographic setting. Now we always, in our presentation of Geology of Sculpting Stone, talk about what the Earth looked like. Well, since on a geologic basis, the flows of the Columbia River basalt sheet flows occurred fairly recently, 14 million years ago, which sounds like a long time ago, but not much in overall geologic time. So when we take a look at the continental distribution, you can see the continents look about the same. Here we are in the Middle Miocene, about 14 million years ago. And you can pretty much see and recognize every single continent. Some have a little bit more water on them than others, like in the Mediterranean, but the outline of North America is very much the way we would see it today. And Washington State here is the upper right, so we'll spend a little bit of time talking about that. So here is a more detailed map. The fellow that does this, I think, does this wonderful drafting job of producing a real visceral sense of what the continents look like in time. And here we have a period of time, roughly mid-Miocene. North America is pretty distinctive. Everything looks the same. Obviously, you can see Florida is still underneath water here. That's a whole different story. But up here in the Northwest, you can see we have some major oceanic embayments that come into Washington State, but by and large, the west portion of the United States looks reasonably recognizable. A series of little islands and things that resolve themselves over time. Here I've zoomed in on a spot where the Columbia River basalts formed as I've zoomed down into Washington State. And so they may have formed at a time where there was a oceanic embayment in that portion of Washington State. So they might have encountered some of the flows might have actually flowed out into salt water, and that's seen at the base of some of the flows, which have these pebble basalts affiliated with flowing into water. But that's the distribution of the Columbia River basalts in the paleogeographic world of North America, which on the west coast looks pretty recognizable with a series of more prominent oceanic embayments, which filled in over time and gave us the general look of Washington State to this day. Now, one thing we definitely had involved up here in Washington State that was much more recent is glaciers. And most of you know, of course, that glaciers covered a great deal of North America during the last, say, roughly 10 to 3 million years ago. And to this day, we still may be in the end of a glacial cycle. But the last major glacial cycle occurred about 3 million years ago, a little bit less, and then topped out with glaciers that began to melt as and stay in northern Washington as little as 14 to 15,000 years ago. Now, this formed an ice sheet to the north of us called the Cordilleran ice sheet, ice sheet. And that ice sheet extended all the way from central British Columbia down, filled in Puget Sound as a big lobe of glacial ice. And there was another lobe of it extending into northern Washington called the Okanagan lobe. And among other things, it produced a series of very large lakes in the western portion of Idaho, up around northern Idaho, backing up all the way towards the town of Missoula, Montana. Now, believe it or not, this has been worked out as a series of interesting studies that have showed the distribution of these large glacial lakes. And how these lakes formed is that as the lobes flowed down from north to south, they would dam up old river valleys that were in the area. And behind these glacial dams, large lakes would occur. And some of those lakes, as I mentioned, were in the northern Idaho and western Montana area. And then as the glaciers retreated, sometimes rather quickly, the dams, the ice dams blocking these lakes would rapidly break, and they would flood vast amounts of water across the eastern Washington landscape. Most of you have heard of big glacial floods, the Missoula floods, and their impact, and they would flow all the way across eastern Washington through the ancestral Columbia River mouth all the way out to the Pacific Ocean. Now, what that did is it carved or produced deep channels into the Columbia River basalts that we see today as a series of deep channels or coulees, as they're referred to in the geology of eastern Washington. And that resulted in flow rates by some of these floods, sometimes approaching 65 miles an hour. And these lakes were so large and the floods occurred so quickly that at times it might have resulted in flows that were 10 times the combined rates of all the rivers in the world for a very short period of time. These flooding events occurred about every 2,500 years, and they produced a very dramatic look to eastern Washington. If you've ever been over there to see the very dramatic deep coulees and cut channels and exposed sections of Columbia River basalt that makes up a lot of the topography and scenery of eastern Washington. Now here's a picture of some of the more famous ones: Frenchman's Coulee and the some channels near Othello, Washington, in eastern Washington, actually more towards up around the town of Othello. But here you can just get a sense of the deep valleys that these Missoula floods must have created. And these were carved out very quickly over the space of a few years to maybe a few tens of years. As these massive floods came down, they would have been truly unworldly. Nothing really kind of exists like the floods that are happening there that happened during the Missoula floods back during the last glaciation period. And they produced these very distinctive landforms, these mesa type landforms with deep channels, some of which are hundreds of or over 1,000 feet deep. And these are the remnants of these large Missoula floods that cut right deep into the Columbia River Basalt Group. And in fact, the stratigraphy of the Columbia River Basalt Group would not be known nearly as well if it wasn't for these deep channels that cut down into it that expose so much of them, allowing them to be carefully mapped. Now, what they also did is leave behind areas where they formed waterfalls because of these massive flowing water channels that came from the lakes that were behind mountain glaciers and the glaciers that flowed from British Columbia and broke and formed these massive water floods. And some of these produced waterfalls that would have been extraordinary to look at. They would have dwarfed Niagara Falls. And here we have probably one of the most famous ones, a place called Dry Falls, up to the northern side of the Columbia River Basalt Group. Certainly a place worth visiting if you have never been over to see these spectacular areas. And they are indeed as advertised. They were massive waterfall areas where the Missoula floods would have poured over. But now no water in eastern Washington is flowing like that, not nearly that amount. And so the waterfall has long since gone and left behind the very sharp edge of a cliff face where the water would have flowed to create the very dramatic nature of the terrain now that the water is gone. All right, in our Geology of Sculpting Stone presentations, we always talk about modern analogs. Are there any modern analogs are there any places right now where in the world there are flood basalts occurring? Their answer is no. There are really no flood basalts with big vents producing them anywhere else active in the world. Maybe that's a good reason, because when flood basalts occur, they have a tendency to inject a huge amount of carbon dioxide into the atmosphere. And you think we had global warming problems now. As I mentioned, there were 2 times back in the Deccan traps and then related to Siberian traps where these flood basalts produced so much carbon dioxide they may have wiped out a good deal of animal and plant life at the time and may be tied to mass extinctions pretty directly. Fortunately, today we have no flood basalts doing that and none likely to happen in the near future, but we do have places where we do have some significant, highly active volcanoes which produce a large amount of lava. Here, as I've just shown, Iceland being a classic example near one of the mid-oceanic ridges of plate tectonics. A lot of volcanic action producing basalts, volcanics flowing in that area. Mount Etna, Sicily, active to this day. And in fact, even in historic times, Mount Etna has wiped out a lot of different villages around it, all the way back, notable way back into ancient history. And of course, in our own United States, Hawaii and the Hawaiian Islands are a very famous area for significant basalt activity. By the way, Hawaii and the Hawaiian chain is produced by another hot spot, but that's a whole other story in itself. Now, some of these flows, like the Columbia River basalts, have low viscosity, which is viscosity being a measure of how things flow. And the low viscosity can produce rapid fluid flow that mimics elements of flood basalts, but obviously on a much smaller basis than classic flood basalts, fortunately. Here, just a couple examples of lava, all from Hawaii, I believe, where the nature of the rapidly flowing volcanic material is quite obvious. Now, we close out every Geology of Sculpting Stone series by a look at the art and architecture produced by the stone. And let's start with art. Well, basalt has been carved by ancient man for a very long time. In the Columbia River Basalt area specifically, we find pieces made back in early Neolithic times, although this piece is identified as pre-19th century, but couldn't be dated quite any more exact than that. But we know that ancient North American inhabitants carved Columbia River basalt in a number of different forms. Focusing in on our own association, we have many members who love the Columbia River basalt because it produces a lot of beautiful figurative art as well as abstract, and it polishes to a beautiful black brown color, which is not always easy to polish because basalt being very glass-like shows scratches pretty easily. But when you get it right, it produces a really magnificent sculpture. Here's a piece by our own Sabah. He does beautiful figurative pieces out of Northwest Columbia River basalt. Probably, however, in the membership, the most famous basalt carver has to be Tom Small. Tom Small has created more wonderful Columbia River basalt pieces probably than any member of our association. Massive tower pieces like on the left, working basalt boulders on the right, lower right, and very interesting little abstract pieces, architectural, oftentimes because of his and his father's background, that include leaving behind some of the rind of the basalt. And here is a very distinctive picture of that rind we talked about, which is part of the Columbia River basalt, which he even adds a little bit of gold plate to. But Tom probably is our most qualified and varied and remarkable sculptor of Columbia River basalt. When it comes to architecture, Columbia River basalt, because of its characteristics to break in patterns that are glass or conchoidal shaped and irregularly, don't make it a particularly easy building block to use, but it has been used, and especially in rough forms for all sorts of purposes. Shaping it into dimensional block to easily use is more difficult. However, there are some sculptures, including or structures, including this house in Lake Oswego, built in the early 20th century, and a rather famous old church in Portland in the late 19th century, which have beautiful Columbia River basalt used in them. And I love the color matching they've done to give some real character to the individual blocks of the pieces. Also, Columbia River basalt is used in modern architecture, particularly stone walls, both dry stone stack, rough and more finished, and also used as veneer and housing. And even though historically in the past that stone was difficult to use for building stone because it didn't have flat cleavage faces that could easily be applied as a veneer or be load bearing. Nowadays, there are a lot of suppliers of Columbia River basalts and all sorts of characteristics for tiles and building stones. It's gotten much more commonly used and can make a very attractive stone if you're into dark grays and blacks and browns. So in conclusion, what can we say about Columbia River basalt? Well, it's one of the most popular stones of the Northwest Stone Sculptors Association for three reasons. One, its proximity in eastern Washington makes it a fairly inexpensive stone with a lot of selection to choose from. Two, it can be worked by a number of different tool types, from hand tools to diamonds, electric, and pneumatic. It's actually workable by the complete tool set of the modern stone sculptor. And three, the stone itself, with its interesting rugged rind, its fractured surface for a split surface, and how it polishes up, can make it extremely attractive to incorporate into artistic design for a number of different artistic forms, whether it be figurative or abstract. And then finally, the geology of the Pacific Northwest Columbia River basalt is really fascinating, isn't it? Being one of these flood basalts, rare in Earth's history, perhaps tied to major mass extinctions and other events, make it particularly interesting to tell the story about. And it having such a major impact on the evolution of Washington State, and then being modified by those fascinating Missoula floods that carved the deep coulees and other interesting landforms, makes it a great story to add to your artistic piece, no matter what you're carving, and whether your form is figuratively abstract. It makes a great addition to the story you want to tell about your art. Well, this concludes another Geology of Sculpting Stone. This is Michael E. Yeaman signing off. Till next time.